right? The car initial time is 0. Our final time is, I don't know, 2 hour. Velocity, initial velocity is 0 mile per hour, and final velocity of course is, I don't know, 10 mile per hour. Isaac, can you tell me whether the car is at rest, constant velocity, or is speeding up?
Speeding up.
Okay. You're gonna find the acceleration of the car, and then you're gonna complete these 6 graphs. 1, 2, 3, 4.
Average velocity. Oh, well, no, not the average velocity, but the change in velocity divided by the change in time, which is just going to be 10 minus 0 over 2 minus 0, which makes 5 miles per hour squared. So, then what's the distance over time? Well, it's going to look something like this. Now, how do we actually know where it starts?
Can you start from the origin, please?
How do we actually know where it starts and stops? Well, we know it stops at 2 hours. We know it starts at 0 hours and 0 miles. But then, how do we know the y-coordinate of this point? Well, that's very simple. We use the formula d is equal to d naught plus v naught t plus half at squared. Of course, there's no initial position or velocity since we're starting from rest. And we already know the acceleration is 5. So we just multiply that in, and we get 10 miles. Alright, now displacement is going to be the exact same thing as distance because we're traveling in the same direction the whole time. Speed versus time is going to be pretty interesting. Well, speed and velocity are going to be the same since we're traveling in one direction. Since it's constantly accelerating, we go from 0 at time 0 to 10 at time 2. So since it's a linear correspondence, it's just a line like this. And the same thing is true for velocity. Just have 2 and 10.
You think velocity final is 10?
Yeah. Okay. And the acceleration is always going to be the same. So it's just going to be a constant rate of 5 miles per square hour. So it's always just going to look like this.
Alright. Can you put a dot? Can you use the green to put a dot on the red of DT graph?
Here?
Put a dot on the DT graph, on the red graph, just in the middle. What does this dot represent?
Well, at some specific time t, it was at the position p of t.
So this dot...
The y-coordinate of the dot is the position, and the x-coordinate is the specific time.
This dot give you the location at a given time?
Yes.
Alright. Can you put another dot at later time?
What?
Can you put another dot on the graph at a later time?
Oh.
What does this dot represent?
Well, it's just the position of the same particle at a different later time.
Okay. Now can you connect both dots and make a line, create a line? It takes 2 dots to create a line. Okay. What do you call that red graph? And what do you call this green line?
Well, the red graph is our original position function, also known as a parabola in this specific case. And our green line is a secant line because it intersects the parabola at 2 positions.
Instead of secant line, can you also call it slope?
Yeah, okay.
Slope of a DT
So
graph
it's the average slope of the DT graph over this interval.
Alright, now can you use another color, maybe blue, to create something not secant line, something just touches one point on the red graph?
Okay, that would be called a tangent line, and it's essentially what happens if we try to merge these 2 points to create only one point. So, it would look something like this.
It tells us only at one location.
Yep.
What do you call the green line?
The green line?
Yeah, the green line. What do you call that one?
The green line is a secant.
And what is the blue line?
A tangent.
And in physics, what do you call the secant line? And in physics, what do you call the tangent line?
Average velocity and instantaneous velocity.
Be careful, I'm gonna give you one more chances.
What?
This is dt graph. This is not a displacement versus time
Yeah,
graph.
but we're finding the slope. Oh, right. They are the same in this instance, though.
Okay. So say it again. What is the green one?
The green one is the average speed, and the blue one is the instantaneous speed.
Can you explain it for my student? What are the differences between average speed and instantaneous speed?
Well, the thing is, average speed is essentially what you get when we all know speed is just a change in distance over time, but we're essentially taking the total change in distance and dividing it by the total change in time. But instantaneous velocity is what happens when we take these 2 points and try and shrink them down into a single point. We take the limit of this distance shrinking over time.
When cops pull you over, cops give you a ticket for average speed or instantaneous speed?
Well, instantaneous speed.
Good. Okay, the final thing. Can you redraw this graph, please?
Oh boy.
dt graph. The last thing of our conversation now. Here is the red. This is we're gonna call dt, and this is displacement versus time. Those are missing.
Oh, I must have erased this on accident.
All right. Okay. So now challenge. You're gonna use green. Can you put a circle on the dt graph? Just put a circle on the dt graph.
Green?
Green is good. Oh, before you do that, let me put 1, 2, 3, 4, all the way 6. We have 6 graph. And let's also write which one is second degree polynomial, write 2. Which one is first degree polynomial, write 1.
This is a second degree, this is a second degree, this is a first degree, this is a first degree, this is a 0th degree, this is also a 0th degree.
Okay, good. Now can you circle the distance versus time graph?
The distance versus time graph is right here.
Now can you circle, be careful, can you circle the slope of distance versus time graph?
Should be right here.
Excellent. Can you circle the displacement versus time graph?
Yup, it's this one right over here.
Can you circle the slope of displacement versus time?
Yup, it's right here.
Can you circle the speed versus time graph?
Yup. Okay. I might as well use the same color.
Speed versus time graph.
Sorry. I'll just use the red that we already have. So speed versus time.
Can you circle the slope of speed versus time graph? Can you circle the velocity versus time graph? Can you circle the slope of velocity versus time graph? Why did you decide to circle the speed versus time graph number 5?
Huh? What?
The slope of speed versus time graph,
Well, it's very obvious. This is just the magnitude of the acceleration. This is changing it from a vector to a scalar, because the magnitude is simply taking in the length of our scalar, the length of our vector, not the actual direction. In the same way, in this example, speed and velocity are the same since we're traveling in one direction, but in general, speed reduces velocity from a magnitude and direction to just a magnitude. So that's why these two are different.